I want to talk about the total change in entropy of the Carnot cycle. So the Carnot cycle is an engine cycle made of two adiabats and two isotherms. Heat comes into the engine through the high temperature isotherm, heat is exhausted from the engine through the low temperature isotherm, and no heat is moved along the adiabats. So let's calculate the change in entropy of each one of those processes. For an adiabat, there's no heat. So if there's no heat, there's no change in entropy because there's no heat. So that just leaves A to B and C to D. If we're looking at an isotherm, the change in entropy at constant temperature is equal to the amount of heat that we have transferred divided by the temperature of that isotherm. So our change in entropy, if we're looking on an isotherm, the heat we transfer is equal to the work done by the gas. So the work done by the gas is the number of moles times the universal gas constant times the temperature of our isotherm times the log of our final volume over our initial volume. So that temperature of our isotherm cancels out. So our change in entropy from A to B would be the number of moles times the universal gas constant times the natural log of our volume at B over our volume at A. Now, going from C to D, similarly, our temperature would cancel out, so the change in entropy would be the number of moles times the universal gas constant times the natural log of the volume at D compared to the volume at C. But those ratios, the ratio of the volume at B to the volume at A, is the same as the volume at C over the volume at D. Well, the log of VD over VC is minus the log of VC over VD, so that means that the change in entropy going from C to D is equal to minus the change in entropy going from A to B. So if I add up my entropies, my total change in entropy is 0. And because there's no total change in entropy for this cycle, then we have the maximum possible efficiency for an engine based off this process. And any engine cycle where we could achieve 0 total change in entropy would also have the same efficiency as the Carnot cycle. Unfortunately, that's impossible to do in the real world because of irreversible effects like friction, but there is a similar cycle called the Stirling cycle. Now, the Stirling cycle operates off isotherms and it operates off of isocores. So what we would have would be an engine cycle that looks like that, traveling around, and there would be some net heat transfer along those two paths, but the trick with a Stirling engine is it takes the heat from one isocore and it recycles it to the next isocore through the use of a device called a regenerator. And by storing that heat and then getting that exact same heat back, you limit the change in entropy of the system and you have a high theoretical efficiency engine. Thanks for watching.